Why does a spring push back harder the more you stretch it? Think about pulling a rubber band, pressing down on a car suspension, or compressing a spring inside a peg. At first, the motion looks simple, but hidden inside that motion is one of the most useful force laws in physics, Hooke's law. In this video, we will connect the everyday behavior of springs to a clear mathematical model. We will define the spring constant, use a car suspension example to calculate stiffness, and then explain why the restoring force always points opposite to the displacement. For an ideal spring, the applied force needed to stretch or compress the spring is proportional to the displacement from its unstrained length. In simpler words, if you stretch the spring twice as far, you need twice as much applied force. If you compress the spring 3 times as far, you need 3 times as much applied force. This linear relationship is what makes an ideal spring easy to model. The equation on the slide can be read as the applied force in the horizontal direction equals the spring constant times the displacement. Here, the displacement is how far the spring has moved away from its natural unstrained length. The spring constant, represented by K, measures the stiffness of the spring. A spring with a large spring constant is stiff. It takes a large force to stretch or compress it by a small amount. A spring with a smaller spring constant is easier to stretch or compress. The unit of the spring constant is newtons per meter. That means it tells us how many newtons of force are required for each meter of displacement. For example, a spring constant of 100 newtons per meter means a 1 meter displacement would require 100 newtons of applied force, as long as the spring remains in the ideal range. Notice the difference between the applied force and the spring force. The applied force is the force you exert to stretch or compress the spring. The spring force, which we will discuss more fully in Hooke's law, points in the opposite direction because the spring tries to restore itself. Now let us apply the spring model to the suspension system of a car. The question asks, what is the spring constant for a car suspension system that settles by 1.2 centimeters when an 80 kilogram person gets in? Before we solve it, let us think physically. When the person gets into the car, the person's weight pushes downward on the suspension system. The springs compress until the upward spring force balances the added weight. The car settles downward by a small distance, 1.2 centimeters. Our goal is to find the stiffness of the suspension. In other words, we want to know how much force is needed per meter of compression. A very common mistake in this problem is to use 1.2 directly as the displacement, but the displacement is given in centimeters, while the spring constant should be in newtons per meter. So before we calculate, we must convert 1.2 centimeters to meters. That gives us 0.0120 meters. We also need the force caused by the person. Since the person is at rest, the relevant force is the person's weight, which is mass times gravitational acceleration. The 80 kilogram person has a weight of 80 times 9.8 meters per second squared, which gives us 784 newtons. So the physical story is this. 784 newtons of weight compresses the suspension by 0.012 meters. From that information, we can calculate the spring constant. So the applied force is equals the spring constant times the displacement, and we can rearrange this to find spring constant. So spring constant K is equals to Fx divided by x, and we can substitute the values, so we find the spring constant is equals to 784 newtons divided by 0.012 meters, and that gives us 6.53 times 10 to the power 4 newtons per meter. So the spring constant of the suspension system is about 65,300 newtons per meter. This means that for every meter of compression, this suspension system would require about 65,300 newtons of force, assuming the system behaves like an ideal spring over that range. Since the actual compression is only 0.012 meters, the force needed is much smaller than that full 1 meter value. This answer is reasonable because car suspensions must be stiff enough to support large forces while compressing only small distances. Now that we know how the spring constant connects force and displacement, we can return to the deeper idea of the restoring force and the negative sign in Hooke's law. Hooke's law describes the restoring force exerted by an ideal spring. In spoken form, the spring force equals negative spring constant times displacement. If the object is displaced to the right of equilibrium, the displacement is positive. So the spring force points to the left. If the object is displaced to the left of equilibrium, the displacement is negative, so the spring force points to the right. In both cases, the spring force points back toward equilibrium. This is why the force is called a restoring force. It always tries to restore the spring to its unstrained length. The spring force always opposes the displacement from equilibrium. So that is why we have a negative sign in this equation. The main lesson from this video is this. The farther an ideal spring is stretched or compressed, the stronger the restoring force becomes. And that force always points back toward the equilibrium position. When solving spring problems, identify the equilibrium position first. Measure displacement from that position. Determine the spring constant and then use Hooke's law to find the restoring force.